this particular video, we have a uniform solid disk here that is pivoted here in the diagram at the very top edge, and then it's just going to let the disk kind of fall naturally. And it wants us to find all these different parts, A, B, C, D, and E. If you need to pause it, read it. Otherwise, let's get cracking. Okay. All right, so for part A, it wants us to derive an expression for the moment of inertia about the axis of rotation. So in this particular diagram that's dictated for us, the pivot is left there. So this is, you just have a cylinder here, and then you're just gonna pinch it right there and just kind of let it fall, okay? And as it falls, it's obviously gonna rotate. All right, so to find the moment of inertia for this, you would just have to apply the parallel axis theorem. So the parallel axis theorem, in case you don't know, this is the moment of inertia, or the new moment of inertia, and that is equal to the moment of inertia referencing center of mass plus the mass itself, and then the distance shifted relative to the center of mass. So d here is the distance shifted from center of mass. So as you can see in this particular diagram, the center of mass is right there in the center of the solid disk, and then it got shifted to the very outer edge. So in order for you to do this first part, part A, you have to know the moment of inertia referencing the center of mass through the axis of rotation through the center there. So here I have an image for you. So the I for this particular solid cylinder with an axis of rotation through the center of mass there, that is going to be 1/2 mr squared. So that is your ICM. All right, so I'm going to go ahead and kick in. How far did it get shifted? Well, the axis of rotation is starting from the center, and it got shifted to the very outer edge, and that distance is going to just be a distance r, because from the center to the edge, that's just the radius of the circle. So in this particular problem, I'm just going to go ahead and apply the information given to me. One, the I value referencing center of mass for the solid disk here is once again simply 1/2 mr squared. So that's why ICM got substituted out for 1/2 mr squared. Well, m here generically, that's just the mass of whatever object you're looking at. In this particular case, I replace lowercase m with capital M because the problem uses capital M. If it uses lowercase m, then you can just keep it as lowercase m. So here, because it's dictated for me that the mass of the disk is denoted as capital M, I'm just going to replace little m with big M. Once again, d here is generic. This is the distance shifted. So the distance shifted here in this case would just be a distance of r, because it went from the center once again to the edge. That is the distance of r. So instead of d, I would just call it r, and then that term is being squared. So from here, we can just simplify, just doing fraction here. So this is 1/2, and this is a whole. So if your math is good, a half plus a whole is 1.5, which is 3.5, but I'll just do this properly for you. This has the denominator of 2. The right term doesn't have a denominator, so to add 2 terms, we can just find common denominator. So to get the right term on the right to have a common denominator of 2, you just multiply top by 2, bottom by 2. So as you can see here, both terms now have a denominator of 2, but the numerator is pretty light work. Here you have mr squared. On the right side, you have 2 mr squared. So 1 mr squared plus 2 mr squared, that would just be 3 mr squared, and then the common denominator is 2. So therefore, the final outcome here is just 3 mr squared divided by 2, and that is our moment of inertia referencing the very outer edge where the pivot is. Okay. All right. Now let's go ahead and crack out part B. Part B wants us to derive an expression for the angular acceleration the instant the disk is released. So here's the diagram once again. Well, to find angular acceleration, you essentially have to do torque. Anytime an object rotates, there's some sort of torque involved here. So I'm just going to set up the 2 definitions for torque. Torque here is the force perpendicular to the moment of arm. That little symbol down there, that's just a perpendicular symbol. Keep that in mind as you do torque. You need perpendicular components. Okay. On the right side, this is the second definition of torque. Torque is by definition just I alpha, analogous to F equals ma. All right. So here, in order to find alpha, I need to identify what force is causing this particular solid disk to rotate at this moment. The moment it's released, and then what my r is. All right. So keep up. So here is my f of g. F of g for the solid disk is placed right at the center. So I'm just going to call that f of g. And then, well, how far is this force relative to the pivot? Once again, this pivot is dictated for me. So I'm just going to go ahead and draw this perpendicular arm. Well, what is the length green there? That length is still r, because you're going from center to the outer edge. And these two are already perpendicular. So we say r is perpendicular to f of g, or you can say f of g is perpendicular to r already, so we don't have to do any geometry here. So I'm just going to go ahead and apply it. Well, what is the force that is going to cause this disc to rotate as you release it? Well, that's the force of gravity. Well, how far is it away from the axis of rotation? That's just a distance r for this particular problem. Well, what's your I value? Well, your I value here is what we calculated previously in part A, which is 3/2 mr squared, right? So don't plug in 1/2 mr squared. Do not plug in 1/2 mr squared. You have to use the proper moment of inertia based on where the pivot is. So we calculate in part A, according to the dictated pivot, that moment of inertia for this particular solid disk is 3/2 mr squared, and I'm going to times that by alpha. You notice here, I haven't done anything with alpha because that's what I'm asked to find. So I'm just going to take it one step farther, and that is I want to replace f of g with mass of the disk itself, which is capital M in this particular problem, times g. Everything else stays the same. So I'm just going to go ahead and cancel stuff out. M is on the left side. I see an M on the right side. I see an R on the left side. I see an R square though, right? This is R square on the right side. So I'm going to cross stuff out properly here. I'm going to cross out the square term because R square is R times R. So make sure you don't just cancel things out incorrectly. So it's R squared, so I'm just going to cancel that square term out because this is only one R on the left side. Well, really here, in order to find alpha, all we have to do is multiply both sides by 2. So I'm just going to move the 2 here on the bottom right to the top left. And then I want to divide both sides by 3, or I can just move this top 3 here to the bottom left. And then here we have an R that's being multiplied, so I can also divide it on both sides. So if you do a little movement, a little algebra stuff, so 2 goes up, that means it's 2 times g. The 3 and the r, because they're both in the numerator, goes down to the bottom left, and there's nothing here on the bottom left on the right, left side, so that would just be 3r. Okay, so hopefully algebra is good that this step is super light work. Okay, other than that is your function at the moment it's released. I do want to point out that alpha continually changes because your force continually changes. Okay, all right. So keep that in mind. So for these types of problem, alpha is not constant. It actually changes as the solid disk falls. Okay. Part C. Part C wants us to derive an expression for the angular speed where the center of mass is. All right. So let's do it. In order to do this particular problem, you have to use conservation energy. Why? Because initially the center of mass of the solid disk is at a certain height, and then it's going to be dropped as it rotates. The center of mass is going to be somewhere else, a position lower than where it was. Okay. So here in my work, I have a statement that says PEI, potential energy due to gravity. All of that will be converted to kinetic energy as it's released. So, well, what is PEI? PE due to gravity simply generically is just mgh. Well, m here is capital M because the problem says so. G is just gravity due to acceleration due to gravity. And I highlighted h here because this is usually where folks goof. Okay, so h here have to be applied correctly. So if you can look at my schematic, okay, here I went ahead and put the center of mass there because the center of mass is up here, okay, in this diagram, right? And as it falls, watch my cursor, it kind of traces out this nice arc where it's going to be right there. So anytime you're given a shape, you have to reference center of mass because you treat the shape as a whole. So I'm going to draw a line there that goes through the pivot and the quote unquote where the center of mass first initially is at. And then I'm going to draw a second line. Well, this is where the center of mass is now, right? So as it's going from a horizontal and it swings downward here, where the dashed line is indicates that the center of mass has been displaced. So it's moved downward. Well, how far downward? Well, just using common sense, really, the distance from center to the pivot is just a distance of r, right? So how far has the center of mass fallen? Just a distance r, okay? So I'm going to go ahead and go substitute a couple things out here. So on the left side, instead of mgh, I'm going to actually just call it mgr. Well, h is r because the center of mass has only fallen a distance r. It is a common misconception for people to put in 2r because they're thinking at the very, very outer edge. So that's a big no-no, okay? You have to reference center of mass, okay? So for h, do not put in 2r. That's a big misconception. So the center of mass has only fallen a distance of r based on my drawing there, okay? On the right side, Well, 1/2 is part of the KE rotational. I here we found earlier, referencing the pivot given the problem here is 3/2 mr squared. And you notice here I kept omega squared the same. Okay. All right. So here I'm just going to go ahead and do a little algebra stuff here. 1 times 3 is just 3. 2 times 2 is 4. So that's where that 3/4 comes from. Once again, you notice here I can cancel things out. M on the left side, M on the right side. I see an R by itself. I see an R square on the right side. So I'm just going to go ahead and cancel things out. That M is going to disappear. The M on the right is going to disappear. That R on the left is going to disappear. But once again, this is R square on the right side. So make sure you cancel things correctly algebraically. So really, I've canceled a lot of stuff already. The only thing left here is just G on the left side. I got 3/4 over here, or 3/4. I got an R still, right? And then I got omega squared. But the question is asking for omega. So I need to isolate for omega squared first. So to do that, I'm just going to multiply both sides by 4. So I'm going to bring the 4 on the bottom right here to the top left. And likewise, I want to divide both sides by 3. So I'm going to bring this 3 on the top right to the bottom left. And then also the R, which is in the numerator because it's being multiplied. So I need to divide both sides by R. So that R is also going to join the 3 in the denominator on the left side. So you notice here, you have 4g times 3r is equal to omega squared. We're almost done. So to get omega by itself, you would just take the square root of this whole left quantity, 4g over 3r, and that's it. Okay. I do want to point out that if you want to, I mean, it's up to you. You see this 4 that's in the numerator? You can break it up, right? So therefore, you can say the square root of 4 is just 2. So if you want, you can pull a 2 out in the front. So you can say omega is 2 radical radical g over 3r. So it's entirely up to you if you want to simplify this 4 in the radical and just pull it out. I just left it as that. So hopefully your math is good that you can know that's the same. All right, let's do part D and E. Part D asks us to find the linear speed of the center of mass. And then E wants us to find the linear speed of the lowest point of the disk where it is dashed. So if you can just keep up here. I'm just going to go ahead and do D first. The D is the center of mass, so I'm just going to put the dot there. And that's my V. So it wants us to find V of the center of mass as it's being swung. Okay, so when this disk rotates to a vertical position, how fast is that point moving? Well, to do that generically, we know there's a bridge function between linear speed and angular speed. It's simply by multiplying by that the radius here or the distance away from the pivot. Okay, so I put a note here for you. This is generic. V equals R omega. You just have to make sure you apply this particular function correctly. So let's do part D. Well, to find VCM, I need to find how far is the center of mass relative to the pivot. Well, once again, in this particular drawing is pretty common sense. Center of mass is at the center, and then the pivot is at the edge. So what is that distance? That distance is simply just R. So I'm just going to say V is equal to R. So the lowercase r here just becomes R because that's what it is in this particular problem. And then omega I already found previously in part C. Okay, so if you need to rewind the video, omega is simply the radical of 4g over 3r. But I do want to point out here, you need to kind of see this little trick. You see there's this R on the outside, right? Well, in order for R to be on the outside of the radical, you can visualize going backward. There must have been an R square inside the radical because the square root of R square is R. So you can kind of do a little backward math, okay? So instead of having R on the outside of the radical, I can visualize having R square underneath the radical. Once again, because R square, the square root of R square is just R, right? Now, why am I doing this? I can do this so I can just simplify stuff, okay? This is entirely up to you how you want to do this step. So I want to put that R back underneath the radical, which makes it R square. Well, why? Because now I can cancel the square and the R there out. So really, the only thing left here is just 4gr over 3. Okay. Now, if you want to, once again, as I said earlier with part C, you see this 4 in the numerator, you can totally factor that out, and you can say that it's 2 times gr over 3. And that's entirely up to you. So either one of these expressions I think is sufficient. Okay. So there's that. Now, the other way to do it, if you want to, up over here where my cursor is circling, okay, again, this all depends on your algebra skill. Where I'm circling, well, you don't have to put the r back into the radical sign to make it r squared. If you wanted to, you can multiply the bottom by r, which makes it 3r squared. But what you do on the bottom, you have to do the top. You can multiply the top also by r, right? Because r over r is just 1. Well, if you multiply the bottom by r, it makes it 3r squared. But the square root of r squared would just be r. So you can pull that outside, which will cancel with this r, which actually leave you with the same response. So if you need to listen to that again and try it out on a scratch sheet of paper or something, once again, you could just multiply both top and bottom by r. Multiplying the bottom by r, make it 3r squared. But r squared can be factored out, which would just make it r. Therefore, r here in the yellow will cancel with the r that we just factor out because in the denominator, which will leave you with just 4gr divided by 3, which is the same thing as I have here. Okay. All right, so I'm just going to go ahead and apply this generic function again for part E. Here, E though wants us to find the linear speed, the v tangential at the lowest point. So at the lowest point, this is where the dot is. I need to find that v. And I do want to point out here that I drew this purple arrow a little longer because as you travel away from the pivot, the object or the point mass at those locations travel faster, okay, because it's farther away from the pivot, okay, because this r. So as this r grows, v also grows because omega stays constant. So omega is just one value for any given shape. The only thing difference is that each point masses travel at a different linear speed. So the farther you are away from the pivot, you have a greater tangential velocity or tangential speed. All right, but I'm going to go ahead and call this v. Notice these two v's are not the same. This v here in the red is referencing center of mass. This v in purple here is referencing the lowest point as part E asked for. So I just kept it as v and v, but if you want, you call it VCM for red, and then you can call this like v, I don't know, edge if you want to use subscript, okay? But I'm just going to go ahead and apply generic functions here. Once again, v equals r omega is just generic. I want to apply it. Well, what is r in this case, right? So don't just say r is the radius. R is the distance from pivot to where the point mass is. So in this case, this line that just came up in purple here, right? I want to measure from pivot all the way to where the lowest point, because that's what part E wants. Well, what is that distance? That distance is just the diameter, which is just 2r. So my work here, I want to replace r here, the little r, generically. That's just defined as the distance from pivot to point mass. Well, that distance in this particular part is 2r because that is the diameter. Omega hasn't changed because I derived omega earlier, right? Because omega is one value for the whole entire shape. Therefore, if you want, you can pull this back into the underneath the radical. So this is 2r. Well, I can just square everything. That would just make 2 squared is 4, and then r squared is just r squared. Okay? So once you do that, you can kind of see things cancel out here underneath the radical sign. There's an r squared, there's an r on the bottom here. I can cancel that out. Well, 4 times 4 is 16. The square root of 16 is just 4, so I can pull back that 4 out. So at this point, it's up to you how you want to do your algebra. Okay. All right. So once again, there's a 4 and a 4. That's being multiplied, so I can just factor that out. There goes that 4 outside. The only thing left on the top is just g and r. The only thing left on the bottom is just the 3. So those two terms need to stay underneath the radical. So gr over 3 needs to stay inside the radical. And that is your answer for part E. Okay. All right. Hopefully you kept up with all the algebra manipulations. All right. Stay nerdy. Don't be back.